Welcome to today's lecture on angular momentum. So this is going to be our final lecture on rotational motion. And in this, we are just going to be focusing on our new version of conservation of momentum. But before we get into that, let's go ahead and recap last time. So last time we introduced and looked at our equivalent for force, which was torque. We saw that torque had two different equations. We have one where we have our scalars and the angle between them, which is represented by a phi, or we can introduce this new type of math called the cross product. And with the cross product, we are using the vector forms of the lever arm and the force, and we are getting the vector form of torque out of that. We then were able to look at using that in terms, or torque in general, typically our scalar form of torque, to utilize Newton's second law of motion. And then we also looked at static equilibrium, which combines Newton's second law of motion for translational dynamics as well as rotational dynamics. And with both of those, they have to have a net force or a net torque being equal to 0. Now, when we were dealing with this, we only had one direction and torque to deal with, but you could, in theory, have this in all three directions and the torque as well. So like I said, today we are going to be looking at angular momentum. We are going to be revisiting part of 12.10, which is the vector description of rotational motion, because it turns out angular momentum also utilizes the cross product. So the first and second video are just going to be purely angular momentum. Our third video is just going to be a nice summary of rotational motion as a whole. So when we looked at translational momentum, we had mass times velocity, where velocity being a vector multiplied by a scalar gave us a vector. So we can, we have seen so far the rotational or angular variable for mass and the value for velocity as well. And with mass and velocity, the rotational variable was related to the linear variable by some factor of r. So for v, it is r times omega, and for m, we had moment of inertia, which was I is equal to mr squared. Well, if we combine this and we go through some proof work, which again we're going to be skipping, we have two equations for angular momentum. Here we have our cross product for angular momentum, where the angular momentum, which is given capital L as its variable, is equal to the cross product of r. So this is the distance from, usually this is a full length distance, or where the object is with respect to the center, cross p, which is the translational vector, or the translational momentum. So again, we have the r value being multiplied by the translational variable. Here it says a cross product, but we could also do it where we have these scalar values. And here beta is just going to be the angle between r and p. So for example, here we have something in the xy plane, and here we have our z-axis. So it is some distance from whatever the center is rotating about. Here is our particle, and here is the momentum vector of it, which happens to be purely in the y direction. The r vector is in x and y. And so we could kind of pretend that, we can shift these vectors around to get where the beta vector it is. And then going through and doing the cross product, similar to the torque, the resulting vector is going to be perpendicular to the plane for the other two vectors. So again, mathematically, I'm not going to be testing you on proofs for any of this. It's going to be making sure we know how to use angular momentum in comparison to, when do we use it, how do we use it, and making sure we're doing so correctly. That's why we're doing two examples. So with angular momentum, it is related to torque. So if we go back to thinking about what velocity is, we can accelerate. We can only accelerate when we have a net force. So if we go and we look at this in terms of angular, variables, a change in angular velocity has to come from an angular acceleration, which must come from a torque. So in order to change our angular momentum, we must have a net torque acting on our object. And this is very similar to what momentum had. We very briefly looked at this equation and we said, well, we have to have an acceleration to have a change in velocity. That's all we used it for, and that's going to be continuing what we use it for. However, this is a little bit beneficial to know for the next example, for the second video example. So let's look at the conservation of angular momentum. So as with, we looked at Newton's second law, we looked at, rolling objects, the laws still apply, and we were able there to use them exactly the same. But for the law of conservation of angular momentum, the angular momentum L of an isolated system, so that means net torque is equal to 0, is conserved, and the final angular momentum is equal to the initial angular momentum, where both the magnitude and direction of angular momentum are unchanged. So it's the same idea that we had for translational momentum, where no net force or no external force meant no change. The conservation of momentum could be used. The same is true here. We can use the conservation of momentum if we have no net torque on our object and we don't have any external torques acting on our object. So what happens if we both have linear and angular momentum? Well, when we looked at energy, we just added the two of them together. We added our translational or our center of mass kinetic energy to the rotational kinetic energy. We just added those two values together. We can't do that for angular momentum. We cannot just add the two momentums together. Because if we think about our units for angular momentum, we'll have meters times kilograms times meter per second. We can't just add that to momentum, which is kilograms times meter per second. These two can't be added together because their units are different. So what we need to do when we have both linear and angular momentum is we have to convert all of our momentums to angular momentums. So everything we focus on must be converted to an angular momentum. Then we're going to go through and use the conservation of, in reality, angular momentum, because all we are dealing with are angular momentums. So in this class, we're not going to be looking at weird shapes. We are going to be looking at nice, simple shapes for stuff where we have equations for the moment of inertia, basically. We're going to look at a lot of disk and points dealing with each other. So if you have a fixed axle or axis of symmetry, you can also use the equation L is equal to I omega. So angular momentum equals moment of inertia times angular velocity. You can use this equation if you have a nice symmetrical object, which again, in this class, we are going to be dealing with. So there are going to be some opportunities where instead of using RP sine beta, we can use I omega instead. It's going to be very question dependent. So what it means by, a fixed axle or axis of symmetry. Axis of symmetry means we're rotating about the center of mass and everything is the same with it. So that's what the symmetry axis is. The fixed axle is just what we are rotating about. So that can be something with a hinge, like a door or something like that. So here we can see that if we're using the vector representation of angular velocity, the angular momentum will point in that same direction. For the same reason, velocity and momentum pointed in the same direction. The mass can't change that direction. So let's go ahead and do an example. What I want you to do is pause the video, draw a picture, and think about how would you go through and dealing with this. How would you go through and do conservation of angular momentum for this particular object? So first, let's draw a picture of what's happening. So we have what is referred to as a merry-go-round. So these are circular discs that have these like little handles on them, but we're going to always be ignoring those because it makes our shape weird. So it has a mass. I'm going to use a capital M because it is a larger mass than John. It's going to be 250 kilograms, and it has a diameter of 3.0 meters, which means the radius is 1.5 meters. And we have an initial angular velocity of 20 rotations per minute. Again, we need to convert this, so let's go ahead and do that now before we forget. 1 minute divided by 60 seconds. One rotation is 2 pi radians. We can go through and plug that in. I'm going to leave the pi because, you know, it's convenient. So I'm going to have 2/3 pi radians per second. So I'm going to leave it like this because that way I don't accidentally round too soon. So John runs tangent to the merry-go-round at 5 meters per second. So John is running in this direction at 5 meters per second and jumps onto the outer edge. So John has a mass of 30 kilograms. So I'm going to give him the small m because he is smaller than the merry-go-round. And we want to find the final angular velocity in rotations per minute. So we are looking for omega f. So there's a couple of things we're going to need to do here before we can go through and solve. So we are told that John jumps on the same direction the merry-go-round is turning. So whatever shape that is. So let's draw this from the top. So let's say that this is, I just want to deal with positives. So it's moving, I'm going to say that counterclockwise is positive, and I'm going to have John coming from over here. So this is the top of John's head, and he's running at his 5 meters per second. And jumps onto the outer edge. So he's going to be jumping on to the outer rim of this merry-go-round. So if I think about the momentums I have initially, I have John running. Oops. And I have the merry-go-round, which I'm just do as MGR because that's a lot to write out, is spinning. These are happening in the before case. In the after case, John is on the merry-go-round, and they are both spinning. So when we set up our conservation of angular momentum, in our before case we need the angular momentum of John running, and we need the angular momentum of the merry-go-round spinning. Afterwards, we're going to have the angular momentum of John and the merry-go-round moving together. So we have pretty much everything we need to go through and solve already written down. The last thing we want to do is make sure we know the shape that we're going to be using for our merry-go-round. These are very common, just metal disc. So that means that the moment of inertia we're going to want to use is 1/2 mr squared. So let's go ahead and set up what we have so far in terms of equations. So we're going to have the angular momentum of John plus the angular momentum of the merry-go-round. So this is our before. So this is, well, let's not use red. So this is John. And here we have the merry-go-round. This is going to be equal to somehow, I'm going to need some final moment of inertia times omega f, where omega f is what I want to actually solve for. So let's think about this final angular, or this final moment of inertia. So I know that I'm still going to have the merry-go-round. I'm still going to have 1/2 mr squared. And again, this is my merry-go-round. It's the same one I have here. But I now need the moment of inertia for John. So this is where things get a little bit weird. Because John is human-shaped. And last I checked on table 12.2, humans do not have a moment of inertia that's nicely calculated. And that turns out is because as I change the shape of a body, I'm going to have a different distribution of my mass. So there's no nice shape to use for a human. So because there's no nice shape for a human, it's going to be very beneficial to not treat humans as human shapes. Instead, we are going to treat humans as if they are points. So my final moment of inertia is going to be mr squared, where mr squared is the moment of inertia for a point and in reality, a point and a human are equal to each other in this class. Now, I am going to include a video that I'm not going to be doing because it's something I like doing in person. It's very, trying to record it yourself isn't very fun, so I haven't done it. But there is a video that is going to be included, should be showing up in the lecture videos that I post on Canvas, showing how the moment of inertia of a human can be pretty complicated when dealing with conservation of angular momentum. So if you think about sitting in a chair and you're one of the spinning chairs, you can change how fast you can rotate around by taking your arms out or pulling them in or sticking out a leg or something. It's the same thing that happens with figure skaters. Humans are very weird shapes, so we're going to pretend we are still points, even though everything we've been doing with this chapter says that's wrong, to make it as simple as possible and actually doable for this class, humans are equal to points. So that means we can rewrite our equation. We're going to have RMV plus 1/2 mr, omega I, because that's technically what we have here. And let's make this a capital R, because that's where John's going to jump onto the end. It's going to be equal to, I'm going to rearrange what I wrote because want it to be in the same order. I'm going to have mr squared plus 1/2 mr squared, where again the lowercase m is John, capital R or capital M is the merry-go-round, omega f. I am now ready to go through and solve this question. So omega f is going to be equal to rmb plus 1/2 m, oops, sorry, that should be r squared omega I divided by mr squared plus 1/2 mr squared. So we are now to the point where we can plug in some numbers. So before we get into that, I just want to reiterate what we have done. So we are using the conservation of angular momentum. Our before case is we have the merry-go-round that was already spinning, and John is running and is going to jump on to the merry-go-round, and he has some momentum. We need to take that momentum and convert it to an angular momentum by using, in reality, RP sine beta. We dropped the sine beta part because he was running tangent. So beta is 90 degrees. Sine of 90 is 1. So it's just RP. The moment, so for the merry-go-round, we have an initial angular momentum because it's spinning. So with that, we're using I omega because we're spinning through the middle of our merry-go-round. In the final situation, the two are moving together. So that means that we have a final moment of inertia. That is the moment of inertia of the merry-go-round, which isn't changing, but we're adding John to it. So we are pretending John is a point because that makes our life simple enough that we can actually do it in this class. Once we have that, we can take all of our numbers and go through and plug them in to the equation that we have for the moment of inertia. So let's go ahead and go through and do this. All right, so we're going to plug in our numbers. The radius of our circle was again 1.5 meters. The mass of John was given as 30 kilograms. And he was moving at 5 meters per second. Plus 1/2, the mass of the merry-go-round was 250 kilograms. 1.5 meters squared. And we said that we solved for omega I, it was 2/3 pi rads per second. That's all going to get divided by 1.5 meters squared. 30 kilograms plus half of 250 kilograms. So now we can take all of this and plug it into a calculator. I personally find doing this in 2 steps is a lot easier. So I like to do the denominator first just because it's a lot simpler with what you're dealing with. So then I like to go through, do the top, divide it by the bottom that's in the number that's already in my calculator. So after plugging things into the calculator, I got 2.3342, but this is in radians per second. We are explicitly asked to give our answer in rotations per minute. So we need to go back and multiply that through. So there's 60 seconds in 1 minute. And there are 2 pi radians in 1 rotation. So again, when you're dividing by 2 pi, make sure you are dividing by 2 multiplied by pi. If you do just divide by 2 pi in your calculator, it's probably dividing by 2 multiplying by pi, which is the not desire that you have. So put parentheses around 2 pi when dividing. So when I plug this into a calculator, I got omega f. So my final angular velocity is 22 0.2899 rotations per minute, so RPM. Or if we want to use the correct number of sig figs, which is 2 in this case, 22 rotations per minute is going to be the final angular velocity for this particular question. So in this example, we have combined linear and angular momentum in the same question. We're going to do that again with the next example, but it's a very common type of question we will be seeing in this class, is looking at, okay, we have both types of momentum. We need to convert both into angular momentum in order to do conservation of momentum. So anytime an object is rotating and something is interacting with it, we are using the conservation of angular momentum to solve. So even if, like in this case, John had our standard momentum, he was running in a straight line, he needs to have that converted to angular momentum in order for math to work out appropriately because of units. All right, so that's going to wrap it up for this first video. Again, there's another example in the next video, so we'll have some more practice with this.